action.
My name is Erlend, and my project is about pressure pulsations at the Erlend power plant. Erlend power plant is located in Aust-Agder, next to the river Otra. It's hosted by Agder Energy, and in 2016 they commissioned a new turbine to exploit the available water in a better way. And here you see the picture of the entrance at the new plant. The installed power at the new plant is 44 megawatts. It has a head of approximately 50 meters and a flow rate of about 100 cubic meters per second. The turbine experiences loud noises and vibrations when it's running at part load from 28 megawatts and downwards. And Agder Energy has asked for help to find out what's causing these vibrations and noise. My specialization project is to prepare pressure measurements at the Erlend power plant. I've done this by doing a literature study on pressure pulsations in Francis turbines. And that has included what causes pressure pulsations, what damage they can do, and how to prevent them. I've also done measurements in the water power laboratory, and that has included efficiency measurements and pressure pulsation measurements. There has also been done inspection at the Erlend power plant in order to observe what they have, what they are struggling with, and to find out where to place the pressure sensors for the measurements. An example of what can cause pressure pulsations is rotor stator interactions, or RSEs, which then causes pressure pulsations when the runner blades passes the guide vanes, and vice versa. Another example is draft tube vortex, which happens when the runner is driven at the part load. Then the flow leaving the turbine has a rotary component which causes a swirl in the draft tube. And in the middle of the draft tube, a swirl, or called the vortex rope, may occur, as you see illustrated in this figure. And this also causes a pressure pulsation when it rotates. If the pressure pulsation of the RSEs is close to the natural frequency of the runner, it can cause cracks in the runner blades, as you see here in this picture. And in a worst case scenario, this may lead to the failure of the runner. The draft tube vortex can cause damage to the draft tube wall, and in general, pressure pulsations will cause an annoying noise. An active method of reducing pressure pulsations in the draft tube is to add air. The most common place to add air is through the turbine shaft. Another way is to inject water in the draft tube, angled in the opposite direction of the swirl, and in that way reducing it. A passive way of reducing pressure pulsations is installing fins, as you see illustrated in the right picture. Another way is to install extension cone on the runner hub, and that lowers the starting point of the rope, leaving it less space to develop, and therefore by reducing the pressure pulsation. The measurements were done in order to get experience running the Francis rig, and it was done as a group among the students, as a group. The goal of the measurements were to make a hill diagram where the efficiency is plotted with varying discharge and rotating speed of the runner. We measured, among other things, flow rate, speed of rotation and torque in order to calculate the efficiency. We used these values in a MATLAB script, and it produced this hill diagram as you see here. The pressure pulsation measurements were done with the sensors mounted as illustrated in this figure. It were 3 of them in total. They had a logging rate of 5,000 hertz and a logging time of 100 seconds. We did measurements with the guide vanes varying from 4 to 14 degrees and at a constant RPM. If you plot the signal that we measured, we get this graph, which is in the time domain. As you see it, it's very difficult to read anything from this. So we want to transfer it into the frequency domain, and this is done using a discrete Fourier transform. If we put the data into a MATLAB function, we can plot this, which shows the frequency and its amplitude on the y-axis. From this, we can read the frequency and compare it to the frequency of what we found in the literature study. Yes, to sum up this presentation, Iveland power plant is struggling with vibration and loud noise when running at part load. My project is to prepare pressure measurements at the plant, and I've done this by doing a literature study on pressure pulsations in Francis turbines, and I also done the measurements in the water power laboratory. Yes, thank you.